Good afternoon, everyone. We are ready to begin our next talk. I will be the chair for this session. My name is Scott Glancy. I work for NIST, and I also do a little consulting on the side for Xanadu. Before we get started, I just wanted to ask if Kyle Cerniak is here. If you are, can you raise your hand, Kyle?
He was here.
Okay, good. Just wanted to make sure there were no surprises. Our first speaker for the session will be Victor Albert, talking about quantum spherical codes.
Thank you, Scott. So this has been something that is a problem that I guess I've been thinking about for some time. I guess maybe Leanne can corroborate that we were thinking about how to extend the CAT code, when I was back in grad school. And so this is kind of exciting to me because we finally kind of extended them to multiple modes in, I think, a non-trivial way, and also made contact with linking with classical codes, which was sort of another question that maybe even Rob alluded to this morning, and other people had been asking for a while as to what is the analog of in classical coding theory and the connection to classical coding theory of CAT codes. These were CAT codes that kind of came up, and they had continuous type, syndromes like, with rotations and then also discrete stuff with photon loss. So how do these fit? So we kind of, the purpose of this talk will be to try to relay both of those things. And I'm going to try to keep it pretty simple. The motivation, just as I don't really need to motivate for this crowd, but I'll highlight a quote by Daniel, where he basically says that bosonic codes with multiple modes have not yet really been fully fleshed out if you mod out the concatenated ones, the ones that can be expressed as concatenated ones. And of course, this has been Harrington and Preskill were the ones who kind of pioneered this quantum lattice code constructions, where they do have bona fide things that you can't think of as a concatenated code using very exotic lattices. And we kind of do that now for spheres. So there's kind of two big things in classical coding theory: lattices and spheres in analog classical coding theory, right? And so we take the sphere part and we do the multimode, the multi-dimensional version of that. I'm not going to say the word hypersphere, I'll just call it a sphere. So the take-home message is to try to basically is to interpret the CAT codes as points on a sphere in one dimension or in one complex dimension. So the point is just a complex coordinate with norm 1. And you'll notice that your usual CAT codes, each code word forms a polytope. For the 4-cat, it's just a line segment. For the 6-cat, each code word is a triangle, or the vertices of a triangle, so on and so forth. And the intuition here is just to extend that now to multiple dimensions where you have points on a sphere. So this is an example for our usual 3 dimensions, where we now have more dimensions to place these points on, and we can use these higher dimensions to have more efficient packing of points. You can also, turns out, have 5 tetrahedra whose collective vertices form the vertices of a dodecahedron. And in 2n modes, we are offered a complex n sphere, meaning the vectors of complex numbers in n dimension, such that the whole vector's norm is 1. Okay, those are the ones that form this sphere. And so, for visual purposes, since already in 2 modes we have 4 dimensions, right? So we have the 3 sphere, which we already can't visualize. So all this 2D stuff, is not the largest thing that can fit. So already for 2 modes, we have to go to the 3 sphere. So you're going to see things that are cross sections and you can't really visualize in 4 dimensions, on a sheet of paper. But there's a lot of exciting geometry here that I'll try to convey a little bit and also make contact with actual practical approaches. So let's kind of re-examine a little bit more the details. So that's the take-home message. If you have any questions, let me know. That's the end of the talk. So just some more detail. Let's kind of rehash the CAT code, which I think most of you already know. This is a great pleasure to actually speak in front of this audience. I've loved that this conference has flourished. Let's rehash the CAT code in terms of these polytope language. So each code word is made up of an equal linear superposition of points, which you would call making up a constellation. Each code word has its own constellation. The code has its own constellation, which is the union of all the code word constellations. So there's two types of polytopes here we're talking about. There's a line segment for each code word, and then there's a square here for the two code words, right? So the constellations are labeled by, this it's cal 0, cal 1. And how do you quantify protection from dephasing? Well, an elegant way to do it that gives you numbers that aren't consisting of square roots is just to take the distance, the minimum distance between two distinct points in the code constellation. So that's these two, and square that distance, and then you get 2. So that's how I will be quantifying the protection against rotation errors and dephasing, just by the Euclidean, just straight up distance, no arcs or anything, just straight up distance squared. And I'll call that the resolution because, as you know, as you pump the radius of the sphere, you'll be able to resolve these more and more. Okay, and the degree, the length scale of how much you need to pump to resolve them to a given, amount is quantified by that number, right? So you'll see that as we pack higher dimensions, this resolution can increase because it takes advantage of higher dimensional spheres. You also know that there's this dual source of noise that's kind of dual to rotations, namely losses, and you know that the cat codes will protect here 1 photon loss or 1 photon gain. And you know that you can play this game where you can put more points in each constellation and you can protect against more losses, but then your resolution will decrease because you're packing more points. And it's only a circle, so you can only, pack them as far away as you can using, n-gons. Okay. You know that there's this all sorts of nice little operations that you can put in a Lindblad, or you can drive with a Hamiltonian that do sort of these in this basis Z-type gates and stabilizers. So you'll have a polynomial here in the lowering operators. Here it's just a to the 4th. That thing will annihilate all the points in the code constellation. So sorry, a to the 4th minus alpha to the 4th, and something that will distinguish the code constellations, but not distinguish points within each code constellation. We'll do a logical Z gate. That's a squared minus, that's a squared. You can put that in plus alpha plus a dagger squared. Put that in a Hamiltonian and drive it. And people have done these beautiful experiments, right? The Yale group. I hid all the slide with all the references, so sorry about that. You all know the reference. Go to the zoo. Find it. Okay, so there's also, so now instead of thinking of polynomials of lowering operators, you think of Gaussian operations, right? So now well, it's a polytope, so you can rotate it, right? And make it invariant. So if you rotate it by what, 180 degrees, well, these things just reflect, but they're the same. So that's another X-type stabilizer, that's the parity. And then if you take the square root of that, wow, but now you're exchanging the red and the blue. That's a logical operation, right? Now think these are going to be more generalized Gaussian operations at this point for multiple modes. Okay, so let's graduate to 2 modes now. We're dealing with a 3-sphere, so 2 complex numbers making up a vector of norm 1. The code constellation makes up the analog of a tetrahedron in 4-dimensional space, which is called a 5-cell. The tetrahedron is such that any distances between any pair of points in the tetrahedron is the same. And there's an infinite family of these for each number of modes. The 5-cell is just a warm-up code, or the general actually name is called a simplex. The simplex code is a warm-up code because it doesn't do necessarily so well for 2 modes. Its resolution for a unit radius sphere, so for alpha being 1, which is set to be the reference alpha, its resolution is 3/2. This is lower than that of, say, the 4-component cat. However, it detects 1 more loss than the 4-component cat. So it starts to sort of be a different code here. And again, just to remind you, so each code word constellation contains 5 points, and those are the 5 points logical 0. And the logical 1 is just, again, parity flip logical 0. You can again start cooking up polynomials which provide these potentials in the phase space that are minimized at the 10 points of the constellation, 5 here and 5 here. And in this case, and in more general codes, you need more than 1 now. You need 2 because 1 isn't going to basically cut it. You need more than 1. And so these are the polynomials that act as stabilizers. A and B are the lowering operators of mode A and mode B. Similarly, AB squared acts as a logical. You can start to think through your head of acting with these on these, and you'll see that the reason that this 2 is present is, anyway, it all works out, unless I made a typo. You can play with it in your head. And then the parity operator is, again, just illogical because the constellations are related by sign. And now the 2 here, you have to be careful and put a 2 here. So this is now the stabilizer. It's not a parity anymore. It's almost a parity. It's got 5 different eigenvalues. So you got your 5 syndromes with this thing. Omega is the 5th root of unity. And this is what you would be measuring to detect and correct losses. And if you do this infinite family, you'll be able to see that the resolution gets approaches a constant, that of your 4-cat code, while detecting 1 more loss than the 4-cat code. So, you know, it's a nice intro code. Let's go to something more exciting, like the Hessian code. There's several codes that are sort of like this. There's a handful of these very unique, beautiful polytopes. I'm going to just mention this one because it's very powerful. It has a resolution of 1, same as that of the 6-component cat. Remember, I fixed alpha to be unity. It detects 8 losses, which is the same as that of the 18-component cat. And it corrects 3 losses, which is that of the 8-component cat. So it has very good resolution, but it at the same time can detect and correct losses, which only can be done by the more densely packed cat codes. Okay. And that's again because of multi-dimension. You need 3 stabilizers. There's connection to algebraic geometry here, if anybody knows. You need basically, these are starting to get very interesting here. So you need basically 2 to kind of set the rays, the 27 rays for each of the code words, and then this one to set the radius. Where are we? This is the only one that has alpha in it. These are your logicals. And so here's one thing that the first code that I think we've seen this with is that the degree, namely the polynomial, the highest power term of the stabilizers is less than that of the logicals. So you remember your surface code. This same behavior happens there. You have your ZZZZ stabilizers. These are weight 4, but your logical operation is some big long string, you know, that's weight L. Now, in the original cat codes, your stabilizer was a to the 4th, but your logical was a squared. Here, it's the opposite. Okay, just like this is the case for the LTPC codes. So in some sense, these codes are quantum because you can consider this type of effect as occurring as a result of degeneracy, which is a feature of quantum codes only. And in some sense, these are sort of more quantum because they also have this type feature. See, so the degree of the logical is higher than the stabilizer, not lower. Again, it's made so that you just have 2 Hessians that are reflecting to each other. So this is, again, an easy logical to do. However, now when you get to the stabilizer group, well, then it gets pretty complicated. I won't deny that. The X-type stabilizer group of this code is basically the symmetry group of this compound polytope that's formed by these 2 Hessians for the logical code words. And this is the group that is basically the Q-trig-Pauli group, but it's represented as Gaussian operations. So there's going to be some swaps between modes that generate S3, the permutation group of 3 objects, and there's going to be some phase shifters by cube roots of unity, which is this theta. And this is not even the biggest group that you can pick. I'll get to that later. But so now we start to get really into bona fide Gaussian beam splitter type operations that cannot be written as tensor products of some local rotations or parities. Okay, and these types of more exotic encodings basically come with this type of increase in resources. Something that we haven't yet put out, but I'll just put out for this conference, is some cute way to do logical Z measurements using an extension of the Peg-Barnett phase states. So there's a nice geometrical picture in coding theory, quantum and classical, in terms of packing. And this is basically how error recoveries are done. You have some set of points. In quantum, they're a superposition of points, and you have some noise that moves them around in some way. And then there's these things called Voronoi cells or unit cells that basically tell you how well the code can protect against errors. If your noise has moved you such that each point remains in its own Voronoi cell in the tiling, then you will be able to correct. But if the noise has moved some points outside, then there's a chance that when you snap to the center of the Voronoi cell you're in, you're going to have a logical error, right? So there's this nice geometric perspective for repetition code, for this Hamming cube, for GKP codes, and then for spherical codes, you can also do the same type of tiling on a sphere. This is just notation for sphere, one-dimensional complex sphere. And right, so you have to figure out, so for logical Z measurements, the idea is to try to figure out which set of cells you're in. Are you in the blue or in the white? And that'll correspond to whether you're in the 0 or in the 1, right? And in the one-dimensional case, if you go back to the circle, this was already done in number phase code paper by Josh Ben and Arne. You basically can use a POVM, or projective measurement, constructed using this set of things, what are called Peg-Barnett phase states, which are essentially just rays at a fixed angle in the single mode phase space of the oscillator. They're not normalizable, but they nevertheless can be used as a POVM because they resolve the identity just fine. So in principle, you can measure this. And so these phase states, they resolve, to arbitrary accuracy, anything on the circle. And they can be used to detect, combinations of them can be used to detect whether you're in, this triangle set of triangles or in this other set of triangles, right? So what we've done is something that just extends this to multiple dimensions. And so these spherical states reduce to the phase states when the number of modes n is equal to 1. But they now generalize in a very kind of nice way all of the properties, or most of the properties of the phase states. Namely, they can be used as a POVM, okay? And they have this normalization, which can be written in a much more concise way this way than usually how people write it in terms of I times tangent, whatever. Okay, please don't just do this. And they're basically, they have the core sort of a coherent state with a different weighting factor that depends on the number of photons in a given Fock state, which is this vector L thing. So this thing is what's required to make this work out. And because they have the same type of structure for each total photon number subspaces coherent states, they be transformed the same way under beam splitters and phase shifters. Namely, they're just passively rotated around, sphere. So, and you can cook up spherical codes with these as well, which would be extensions of the number phase codes that were mentioned in Liang's talk. You can try to do normalized versions of them. I'm trying to figure out how to get a good normalized version that actually minimizes some metrology thing. I haven't yet done that. And then if you if you split this sphere up into two regions, one the union of all the blue things and one the union of all the white things, then if you do like a POVM measurement on just those two regions, you'll be able to figure out whether you're in logical 0 or logical 1. It's just one simple application of this. Okay, so there's I mentioned stabilizers are getting a little complicated because they're bona fide Gaussian operations. So let's jump into that a little bit. So we considered polytopes. There are more general ways to consider quantum spherical codes. There's apparently going to be a talk about that later in the conference. So I'm very excited about that. We also considered uniform superpositions, and you can also consider non-uniform superpositions. But let's just stick to polytopes and uniform superpositions for now. And because that will come with some symmetry groups. Each code word polytope has its own symmetry group. And then the collective union of all the vertices of the code word polytopes, the code polytope, has its own symmetry group, G. For example, for the 6 component cat, the symmetry group of each triangle is Z3. Together, that gives you Z6. But the symmetry groups don't have to be abelian. And they don't have to quite be the same. They can be related by conjugation. Well, anyway, modulo that complexity aside, let's just look at how do we use these symmetry groups to extract stabilizer groups and logical gate groups for the codes. The stabilizer group is something that needs to leave each code word invariant. So it can't do logical gates. So it can't permute the code constellations. and it needs to leave each code word constellation invariant, not just the code constellation, but each code word constellation. And this is formally what's called the core of the H subgroups in G, but you can just define it as the intersection of all the elements that are inside each of the code word polytopes. And sometimes the issue here is that sometimes this group can be small. And if you then mod out the whole thing that we get with our polytope by all the things that don't do anything, you get things that do some logical operation. Okay. And I'm just going to show you two examples here where to show you the drastic difference between sizes of these groups that these groups can reach. So one, again, is this Hessian qubit. This has a very big stabilizer group. This is just some polytope stabilizer group notation. It's got almost 1,300 elements. Okay. And this Z2 is for the two lot, is just the parity operator. So and it turns out everything but the parity operator stabilizes each Hessian. So this Hessian and the one that's inverted. And so there's a whole bunch of stabilizers, 648 stabilizers. And that means there's only one, well, there's 648 ways to do a logical X as well, because it's two cosets of Z2 in the group, right? But the type of logical operation you can do is only permuting the two code constellations. So now the opposite can be true. Thanks. So now we're going to do a 5-dimensional qubit logical encoding. Each code word constellation is going to consist of 24 points, similar to the initial paper by Anthony Leverrier and Andre, sorry, Ori. Yeah, I'm going to mispronounce, but yes. That was partially the motivation for this more general framework. 24 cell embedded in 2 modes, so 24 vertices. Together they make up this. So this is kind of like a tetrahedron. This is kind of like a dodecahedron. Fit 5 of these into this thing in 2 modes. Okay, so you get a qubit, 5 dimensions. The symmetry group of this thing, G, is binary icosahedral group. Stabilizer group is super small. It's only one operation effectively that leaves the stabilizers. Leaves the code, each of these 5 things alone. And the rest of these will wind up permuting them in some non-trivial way, realizing a permutation representation of the icosahedral group in only 2 modes. So this is kind of interesting from a coding theory perspective, because there's lots of qubit codes that people try to do sort of transversal families of gates, realizing large groups. But if you do continuous variables, you can already realize the crazy one with just 2 modes using what I would call the analog of transversal in continuous variable language, which is just Gaussian rotation, right? And so you see here that these groups can be quite different, and the stabilizer group here is also quite different. And this presents a problem when you want to decode. This code is very powerful. It can correct lots of different losses, but there's only one syndrome that comes from measuring these Gaussian operations. And this is an issue because you're not going to be able to resolve all these syndromes by just measuring these Gaussian operations. Okay, CSS. So that was the polytope story. And now I want to mention something that's very applicable to some of these modern designs for computers, namely concatenating code. So we're back to concatenating. But what we do is interpret this concatenation from the lower level bosonic framework instead of from the upper level qubit framework. So instead of jumping directly into qubits by just extracting some T1s, T2s on each of the modes and going up to the larger outer code that's discrete, we're going to stay in the lower continuous variable domain. And we're going to think of this concatenation of a qubit code with the two component cat code, and which can alternatively be expressed as this antipodal mapping, where each 0 coordinate of each qubit is just mapped to alpha, and each 1 coordinate is mapped to minus alpha. And in this case, we can interpret now these concatenations as QSCs. The distance is slightly different, but both distances against rotations and against photon losses can be inferred from the distances dz, dx that are given in a given qubit CSS code. The distance dz protects against z errors, and if you concatenate with cat codes, it will protect against or will detect loss and gain monomials that act on dz minus 1 modes. The dx
QSC.
Quantum spherical code. The dx code distance transforms into a resolution remember the distance between two shortest points, two closest points, very linearly, just 4dx over n, because the Hamming distance between qubit states translates very naturally into Euclidean distance between coherent states under this antipodal mapping. And you notice that if you're asymptotically good, this is a constant. Now, the most interesting part that I think this can contribute to, this interpretation can contribute is Z-type stabilizers. So 0 gets mapped to alpha, 1 gets mapped to minus alpha, Z gets mapped to A. Okay, and this hasn't been appreciated, which is a bit, I think this should be appreciated, because if you have a concatenation of a CSS code with a two-component cat, you can use the CSS Z-type stabilizers to cook up jump operators that are going to do same type of dephasing protection that your usual, two A squared type stabilizers do for each mode, but now they do a global one. Okay, and you can get the recipe for which ones to construct by just mapping all the Z-type stabilizers into these products, these lowering operators. For QLDPC codes, these are few body. Okay. And of course, you can do gates, but this is not as, I think, scalable because if you do some surface code gate, it's a product of things in a whole chain, and that I'm not going to claim is very particularly useful, but for small codes also it could be useful. And then X type, so Z gets mapped to A, X gets mapped to parity. So you can likewise map your X type stabilizers to parity operators, right? And gates. Okay, so this is a very simple recipe that you just have to look under the hood of the bosonic code and the concatenated code, and you get these for free, basically. Right. So here I want to just briefly mention that what are spherical codes? They're just points on a sphere. These points can be in any configuration space you want, as long as there's some spherical geometry that's physically reasonable. We don't have to use coherent states. We can use spin coherent states. We can use pair coherent states, which I think would be a fun combination of these types of paradigms. This, of course, was motivated in part by sort of previous work on these molecular codes, and you can also interpret these in that same way. You just have to be careful about what you consider as the analog of loss errors. It's some potential on the sphere that you have to think about. Either you express it as spherical harmonics or some monomials of loss operators or something. And that's so basically it. I'm happy to discuss about applications of this thing. And want to highlight these Z-type Lindbladians could potentially be useful because they're at least scalable and they provide extra protection against dephasing. And I want to say that this is sort of a more general framework that I hope will be explored by the community some more. So with that, I want to thank you for your attention.
All right, who has questions? A couple of people in the corner.
Hi, yeah, thanks for the nice talk. Just a question on your logical Z measurements. So after you use these generalized phase states to measure some angle, you still need to solve some version of the closest vector problem or something like that on the sphere in order to get the right logical output, right?
Yeah, so it's not, it might be difficult to do for large dimensions, you're saying?
Yeah. Yes.
Yeah. Yeah, I would agree.
Have you thought about how these spherical states look like for concatenated codes? Can you get decoders for qubit level codes from that?
How would you concatenate?
I mean, using your prescription there, the CSS.
Oh, the antipodal mapping?
Yeah.
Short answer is no. I haven't thought about decoders. So sounds like an interesting question. I don't know if anything smart to say. What you mean, analog type information using decoders, like that use the analog information in a more efficient way? Yeah, yeah. Yeah, I'm sure that there's something there. Because again, it's continuous, and so you want to discretize it in a smart way, right?
Yeah, fun way of making it.
Yeah.
Thanks.
Maybe this is an ill-informed question, but you're in this slide where you turn the Z-type CSS stabilizers into Lindbladians. Is there any way to turn it into a sum of annihilation operators instead of a product? And would there be any value in that?
There would, yes. And I don't know how to
There
do
would be value in it, but there's no way yet.
that I know of. I try, I mean, yeah.
Okay, I'll think it over at some point. Thanks.
Hello.
Hello.
So I think that one of your premises is that you define the logical error like a distance at the level of the code space. Now, I can give you an infinite amount of Hamiltonians and Lindbladians that have that same code space as the stable state. Would you say that they all have the same logical protection? It's really the distance at the level of the code space that where we should be looking at.
Well, I don't know what you should be looking at, but I was looking at it this way because a code usually comes with features that allow it to protect against noise that are quantified by some parameters. And I guess the takeaway here, when maybe something already people knew in one mode, is that CAT codes have two parameters. They basically have a continuous one that quantifies some resolution between the coherent states, and then a discrete one that quantifies how many losses you have. This is not the whole story. You need to figure out how to decode things, how to do logical operations. But the spherical code framework that we have is basically, at least the paper that we put out is for the most part looking at just a table of all these codes and their corresponding parameters and stabilizers and logicals without getting too much into detail about decoding, for example. Not sure if I answered.
Kyle? Maybe we can have.
So it's going to be very short. I missed an important point of information. When you go to higher dimension and you fix alpha, does alpha square is it still like the total photon number in all the modes or not?
Yes, alpha is now a vector.
But it's still like if I square alpha, I get the total
If
number
you
of photons.
square, you take the norm squared of alpha. That is, to me, the total photon number. However, you have to kind of interproduct that with the frequencies, right? Like it's really the frequencies also contribute to the energy. So it's really should be like, the frequency should be like a little matrix frequencies in between the alpha vector and the alpha vector. Because the total energy is sum of omega I and I.
So when you talk about protecting against more losses, for instance,
Yeah.
You don't have more losses because you go to higher dimension. If you fix like the photon loss rate of every more losses because you go to multimode.
Well, you get this combinatorics. Where did the losses happen? Did all four happen on one mode, or did one happen for each mode, right? So we have to, right? The way there's, you know, if you have n modes, there's a lot of ways to distribute four into n different buckets, right? So we have to worry about four losses, for all combinations of four losses in all modes. So there's more errors in that sense, right? But alpha squared is, yes, it's the radius of the sphere if you ignore this frequency.
I can
Yeah.
talk later.
Yeah, let's talk.
Thank you, Victor. Next, we have Kyle Cerniak, who will tell us about characterizing coherent